A cold April morning, 1945. American soldiers enter a factory in Jena, Germany. What they find there will change the history of technology forever. Lenses so precise, they're 20 years ahead of their time. Microscopes that make the impossible visible. Optical systems whose secrets the Allies desperately want to understand. This is the story of Carl Zeiss, the German optical empire that conquered the world, even after its factories were dismantled. Its scientists abducted and its patents stolen. During World War II, the name Zeiss meant absolute optical superiority. While Allied pilots struggled with blurry scopes, German bombers saw every detail from 26,000 feet through Zeiss optics. While American submarine periscopes failed in bad weather, German Zeiss periscopes pierced fog and darkness with crystal-clear precision. The technological gap was so huge that Allied commanders issued secret orders. Zeiss equipment had absolute salvage priority, more important than enemy documents, more important than captured officers. A single Zeiss gun sight was more valuable than an entire tank. But how did a German optics firm become so dominant? The story begins in 1846 in a small workshop in Jena, where Carl Zeiss had a revolutionary idea. What if optics wasn't just craftsmanship, but precise science? He partnered with physicist Ernst Abbe and chemist Otto Schott. Together, they developed mathematical formulas for lens design, special types of glass with controlled optical properties, and manufacturing techniques with tolerances measured in microns. By 1900, Zeiss was the world leader. German precision had conquered optics. When the war began in 1939, Germany had a technological lead of a decade in optics. Zeiss scopes on German tanks allowed precise shots at 2,000 meters. Allied tanks had to get within 800 meters. Zeiss binoculars at German observation posts spotted enemy movements before Allied scouts even knew they were being watched. In the Luftwaffe, Zeiss bomb sights were so precise that German bombers hit strategic targets from high altitude, while Allied bombers had to fly low, exposing themselves to massive anti-aircraft fire. The British Admiralty wrote in a classified report in 1942, German U-boat periscopes with Zeiss optics give the enemy a decisive tactical advantage in night and bad weather operations. Our periscopes are virtually useless under the same conditions. Allied engineers dismantled captured Zeiss equipment, trying to understand its secrets. But it wasn't just one component, it was the entire system. Special glass, precise coatings, perfect lens design. Micron-level manufacturing. Every attempt to copy Zeiss failed. The copies were always inferior. An American technician described his frustration in 1943. We measured every part, analyzed every material, documented every manufacturing step. Our reproduction looks identical, but when you look through it, the difference is night and day. German optics are simply sharper, clearer, more precise. It's as if they have access to physics we don't understand. Zeiss produced over 2 million optical devices during the war, 820,000 binoculars for the German armed forces, 340,000 scopes for tanks and artillery, 180,000 periscopes for U-boats, 95,000 bomb sights for the Luftwaffe, 60,000 rangefinders for the artillery, plus hundreds of thousands of microscopes, telescopes, cameras, and medical instruments. Every single device had optical quality that surpassed Allied equivalents. The production numbers show the industrial power, but the real story lies in the quality. A British tank commander wrote after the Battle of El Alamein in 1942, German tanks opened precise fire on our positions from distances where we couldn't even see them clearly. Our crews reported that German scopes provided much brighter and sharper images at the same magnification. At dusk, When our optics failed, German tanks continued to operate with full effectiveness. The Zeiss superiority was based on 3 scientific breakthroughs that competitors couldn't replicate. First, special glass with precisely controlled optical properties. Otto Schott had developed glass compositions that combined minimal dispersion and maximum light transmission. This glass required special melting furnaces and extremely pure raw materials. Allies could chemically analyze the glass, but replicating the manufacturing processes was impossible without decades of experience. Second, optical coatings. Zeiss scientists developed thin coatings on lens surfaces that minimized reflections and maximized light transmission. These coatings, often made of exotic materials like rare earth fluorides, were vapor deposited in vacuum chambers with nanometer precision. A coated Zeiss lens could transmit 20–30% more light than uncoated Allied optics. In twilight or bad weather, this advantage was war-winning. Third, mathematically optimized lens design. Ernst Abbe's formulas allowed Zeiss engineers to calculate complex lens systems that simultaneously delivered minimal aberrations, maximum resolution, and large fields of view. Allied designers were still working with trial-and-error methods. Zeiss calculated perfect designs on the drawing board, then manufactured them with micron-precise accuracy. Let's get specific. Take the Zeiss scope Zielgerät 1229, known as the Vampire. This device revolutionized night combat. German soldiers could operate in complete darkness with infrared scopes. While Allied troops were practically blind, the system used an infrared lamp and a special Zeiss image converter tube. The optical quality was so high that German shooters could accurately target enemies at 400 meters in pitch-black night. Allied soldiers reported nightmarish experiences. An American infantryman from the Battle of the Bulge in 1944 described, "We heard shots in the darkness. Our men were falling, but we saw nothing, no muzzle flashes, no movement, nothing. It was as if we were fighting ghosts." Only later did we understand that the Germans had night vision devices, technology we didn't even know existed. In the German Navy, Zeiss optics were even more dominant. German U-boats, or submarines, deployed periscopes equipped with Carl Zeiss lenses, which, under poor visibility conditions, outperformed Allied periscopes by several factors. A 1943 British Admiralty report quantified this difference, stating that during twilight or overcast skies, German U-boat commanders could identify enemy ships at distances, where British periscopes revealed only blurred shadows. This advantage granted German U-boats a decisive tactical edge. In selecting attack positions and timing, Lieutenant Commander Werner Henke, one of the most successful U-boat commanders, wrote in his diary, "My Carl Zeiss periscope is my most valuable instrument. In critical moments, when visibility is poor, it provides information that decides between life and death. I can identify enemy escorts while they are still searching for me. I can observe convoys without them detecting my periscope's position. The optical clarity is simply unrivaled." The Luftwaffe, or German Air Force, perhaps gained the greatest advantage from Carl Zeiss technology: bomb sights, such as the Lotfe 7D, enabled precision bombing from high altitudes. This device, fully equipped with Carl Zeiss optics, automatically calculated the bomb release point, considering altitude, speed, wind, and target velocity. The optical quality was so high that bombardiers could hit targets from 26,000 feet, or nearly 8,000 meters, with an accuracy that Allied bombers required them to descend to 10,000 feet, approximately 3,000 meters, to achieve. An American B-17 pilot, after the war, compared the systems. "We used the Norden bomb sight. which was touted as a wonder weapon. But when I saw and tested German equipment after the war, I realized just how superior their optics were. The Carl Zeiss system provided a clearer, brighter image, with a larger field of view, under combat conditions, with stress and poor visibility. These factors made the difference between a hit and a miss. But Carl Zeiss wasn't solely dominant in military optics. In the medical field, German microscopes were unmatched. Carl Zeiss microscopes with apochromatic lenses delivered an image quality that Allied instruments couldn't achieve. German pathologists and researchers could observe cellular structures that remained invisible in Allied microscopes. This optical superiority gave German medical research a technological head start. In astronomy, German observatories used Carl Zeiss telescopes, among the most precise in the world. The Carl Zeiss Planetarium in Jena, opened in 1923, was the first modern projection planetarium globally. Its optical and mechanical precision was so impressive that after the war, both American and Soviet teams attempted to seize the technology. The manufacturing precision at Carl Zeiss was legendary. Each lens was individually ground, polished, and measured, with tolerances in the micrometer range. Workers at Carl Zeiss underwent years of training. Master opticians required a decade of experience before they could produce the most complex systems. This craftsmanship, combined with scientific precision, created products that industrial mass production couldn't replicate. An Allied production engineer, inspecting Carl Zeiss factories in 1945, wrote in astonishment, "We use mass production methods with interchangeable parts and minimal hand labor. Carl Zeiss combines industrial production with artisanal perfection. Each device is individually inspected and adjusted. This is more time-consuming and expensive, but the result is qualitatively superior. We cannot adopt these methods. Our industry is structured differently." This production philosophy made Carl Zeiss expensive, but also superior. A Carl Zeiss binocular cost 3 times more than an American equivalent, but the optical performance justified the price. Military procurement officers worldwide preferred Carl Zeiss when they prioritized quality over cost. Before the war, Carl Zeiss exported to over 80 countries. German precision optics was a global hallmark. The outbreak of war changed everything. Carl Zeiss was completely converted to military production. Civilian exports ceased. The entire capacity served the German armed forces, or Wehrmacht. Forced laborers and prisoners of war supplemented the workforce. Production multiplied, but the quality standards remained. Even under wartime pressure, Carl Zeiss produced optics that surpassed Allied peacetime production. Allied bombing specifically targeted Carl Zeiss factories. American and British bombers flew dozens of attacks on Jena, but the factories were partially underground, partially decentralized. Despite massive bombing raids, Carl Zeiss continued production until the last day of the war. The resilience of the German arms industry was remarkable. Even under total air war, critical production lines continued to function. An American bomber commander noted, frustrated, "We dropped hundreds of tons of bombs on Jena. Reconnaissance photos show massive destruction, but intelligence reports confirm that Carl Zeiss continues to produce. They have backup facilities, hidden workshops, decentralized manufacturing. This industrial tenacity is impressive, albeit frustrating." As American and Soviet troops advanced on Jena in 1945, they had a clear mission: secure Carl Zeiss. Not just the factories, the scientists, not just the equipment, the knowledge. The city was divided into occupation zones, but both sides fought over Carl Zeiss. American special forces systematically dismantled production facilities. Soviet agents recruited Carl Zeiss scientists, sometimes by force. British commandos confiscated patent documents and research records. An American officer of the technical intelligence teams wrote, "The Carl Zeiss factories are a scientific goldmine. We found production techniques that are years ahead of our best companies, optical designs that should be theoretically impossible, material compositions that our chemists haven't even dreamed of, orders from above, secure everything, document everything, bring everything to America." Over 200 Carl Zeiss scientists and engineers were recruited or abducted. Some went willingly to the West, others were lured with promises. Some were simply taken to the Soviet Union. Dr. Wilhelm Schaller, a specialist in military optics, was taken to Moscow by Soviet agents in 1945, where he built the Soviet optics program. Dr. Alexander Smakula, who developed the Carl Zeiss coating technology, went to the USA and worked for American optics manufacturers. The Carl Zeiss factories in Jena, now in the Soviet zone, were dismantled. Machinery, tools, even entire production lines were shipped to the Soviet Union as reparations. What couldn't be transported was meticulously copied. Soviet technicians photographed every machine, measured every tool, and documented every manufacturing process. In arsenals from Krasnogorsk to Kiev, new factories sprang up, exact replicas of the Carl Zeiss facilities. In the West, Zeiss managers, who had fled to West Germany, established new works in Oberkochen, but without the Jena factories, without many specialists, without access to decades of research, they had to start from almost scratch. Ironically, there were now two Zeiss companies, Carl Zeiss Jena in the east and Carl Zeiss Oberkochen in the west. Both claimed to be the true legacy. Both used the Zeiss name, and the legal battle lasted for decades. But the Zeiss technology lived on, often hidden within the products of other companies. The Soviet optics firm, Lomo, produced camera lenses that were exact copies of Zeiss designs. American firms, like Bausch and Lomb, integrated Zeiss principles into military targeting systems. Japanese manufacturers, like Nikon, based their early products on licensed Zeiss patents. The technical DNA of Carl Zeiss spread worldwide. Today, 80 years after the war's end, Carl Zeiss technology is everywhere. NASA space telescopes use optical principles based on Zeiss research. Medical microscopes in hospitals around the globe utilize Zeiss designs. Smartphone cameras from Apple, Samsung, and Sony contain lenses whose coated surfaces directly stem from Zeiss patents. Military targeting systems in American, British, and French arsenals use optical formulas that Ernst Abbe developed over 100 years ago. If you own an iPhone or Samsung smartphone, you're holding Carl Zeiss heritage in your hand. The camera uses multi-element lens systems with anti-reflective coatings. This technology comes directly from Zeiss innovations from the 1930s, the mathematical formulas that optimize lens curvatures and distances are variations of Abbe's original equations. Modern computer simulation has accelerated the process, but the fundamental principles are identical. In the semiconductor industry, Carl Zeiss lithography systems are indispensable. The ultra-fine lenses that project nanometer structures onto computer chips represent the ultimate evolution of Zeiss precision. A modern Carl Zeiss lithography lens costs over $100 million and is the most complex optical system ever built. But the basic principles, extremely precise glass, mathematically optimized design, perfect coatings, come directly from the legacy of Carl Zeiss, Ernst Abbe, and Otto Schott. Medical technology owes Carl Zeiss an enormous debt. Modern surgical microscopes that neurosurgeons use for millimeter-precise procedures are based on Carl Zeiss designs from the 1950s, which in turn were built on wartime technology. Ophthalmologists around the world use Carl Zeiss slit lamps for eye examinations. Pathologists diagnose cancer with Carl Zeiss microscopes. German optical precision saves lives every day. In astronomy, Carl Zeiss telescopes are legendary. The 200-inch Hale telescope at Mount Palomar, for decades the largest telescope in the world, used Carl Zeiss-inspired optical designs. Modern space telescopes, like the Hubble, use mirrors and lenses, whose manufacturing tolerances are directly derived from Carl Zeiss standards. The ability to observe galaxies billions of light years away is based on optical precision, perfected in Jena, Germany. Even in the entertainment industry, Carl Zeiss is present. Hollywood movies are often filmed with Carl Zeiss camera lenses. Cinematographers appreciate the optical quality, the characteristic rendering, the precise focusing. When you see a blockbuster in the theater, you're likely seeing images captured through German optical artistry. But let's pause for a moment. This story isn't just about technology and patents, it's about people, German engineers and scientists who worked with precision and passion, Allied soldiers and technicians who recognized and respected this superiority, researchers worldwide who built upon these foundations. Technology always has a human story. The irony is remarkable. Germany lost the war totally, cities destroyed, industry dismantled, nation divided, but the technological DNA survived and spread. Carl Zeiss knowledge was not destroyed, it was absorbed. Soviet optics, American precision instruments, Japanese cameras, all carried Carl Zeiss genes. The loser of the war became the technological father of post-war optics. A Japanese optical engineer explained in an interview, "In the 1950s, we studied German patents intensely. Carl Zeiss was our teacher. We learned from their designs, their manufacturing methods, their quality philosophy. Japanese optics today are successful because we built upon German foundations and developed them further. We respect this legacy." This story reveals something fundamental about technology. True innovation cannot be destroyed. It can only be transformed, spread, evolved. The Allies didn't try to eliminate Carl Zeiss. They tried to understand it, to copy it, to integrate it. That is the ultimate acknowledgement of superiority. Leica, the famous camera manufacturer, licensed Carl Zeiss optics for decades. Sony still uses Carl Zeiss branded lenses in premium cameras today. Even Chinese optics manufacturers produce designs that are recognizably based on Carl Zeiss principles. The entire modern optics industry stands on foundations laid in Jena, Germany. A modern optical engineer explained, "If you design a lens system today, you use mathematical formulas that ultimately trace back to Ernst Abbe's work. If you need glass with controlled optical properties, you use compositions that Otto Schott developed. If you coat lenses to minimize reflections, you use techniques that Carl Zeiss perfected. The whole industry is based on German innovation from the early 20th century." Let's delve even deeper into the technical details. The Carl Zeiss formula for achromatic lenses, developed in the 1880s, corrected chromatic aberrations so effectively that it remains the industry standard to this day. The principle: combine two lenses made of different types of glass, whose dispersion properties compensate for each other. Sounds simple, but the implementation requires extremely precise glass, and micrometer-accurate manufacturing. Modern smartphone cameras use 6, 7, sometimes 8 lens elements. Every element must be perfectly aligned, every surface optimally coated, every curvature exactly calculated. The software that designs these systems uses algorithms based on Abbe's Sony condition and his aberration theories. The digital revolution has increased computing speed, but the fundamental optics physics comes from Jena, Germany. In lithography for semiconductors, Carl Zeiss is now a monopolist. ASML, the Dutch manufacturer of EUV lithography machines, relies exclusively on Carl Zeiss optics. Each lens contains dozens of mirrors, each polished with atomic precision. A single scratch in the nanometer range would render the entire system unusable. This manufacturing tolerance surpasses even wartime standards by orders of magnitude. But the principles are identical: extremely pure material, mathematically perfect design, micrometer-precise manufacturing. The economic significance is enormous. The global optics industry has an annual turnover of over 50 billion euros. Carl Zeiss itself employs over 35,000 people worldwide, generating billions in revenue annually. But that doesn't capture the indirect impact. Every smartphone, every computer, every medical diagnostic device uses optical components, whose design principles are based on German heritage. The technological reach is immeasurable. An American defense analyst wrote in a classified report in 1950, "The Carl Zeiss technology we captured in 1945 has advanced American optics firms by a decade." Military targeting systems that we produce today would have been impossible without this technology transfer. We not only conquered equipment, we absorbed an entire scientific tradition. The strategic value of this operation surpasses many conventional military victories. This statement reveals an uncomfortable truth. Technological superiority is sometimes more important than military victories. Germany lost the war, but its technological ideas conquered the world. American soldiers entered Carl Zeiss factories as enemies, left them as students. The victors learned from the vanquished. That's the real story of 1945. In Soviet archives, now partially accessible, you can find fascinating documents, reports on dismantled Carl Zeiss facilities, detailed technical drawings, lists of recruited scientists. The Soviets understood. Whoever controls Carl Zeiss controls the optical future. They invested massively in the reconstruction of Carl Zeiss Jena in the east. The city became a scientific center, protected and fostered, because the optical industry was strategically critical. A former East German engineer reported, "Carl Zeiss Jena was legendary in the Eastern Bloc. We produced optics for Soviet military systems, for space exploration programs, for scientific institutes. Despite the communist planned economy, we maintained high-quality standards. The tradition of precision and excellence survived political systems. That was our pride." After German reunification in 1990, the two Carl Zeiss companies finally merged. Carl Zeiss Jena and Carl Zeiss Oberkochen, separated for 45 years, became one again, symbolically and practically. The optical DNA that was split in 1945 was reunited. Today, Carl Zeiss is a global technology leader, but its roots lie in that small Jena workshop where Carl Zeiss began his vision of scientific precision optics in 1846. History teaches us, true innovation survives. Wars destroy factories, kill people, change borders, but ideas, especially brilliant technical ideas, are immortal. They are copied, adapted, further developed. They spread across continents and generations. Carl Zeiss Optics is more than a product. It's a technological meme that has replicated itself in the global industry. If you found this video interesting, if you're fascinated by stories about technology that changed the world, then you should learn more about other German innovations, jet engines, rocket technology, synthetic fuel. All these technologies have similar stories. German engineering during the war was leading in many areas. The post-war history is often a story of technology transfer and global dissemination. Consider this. How many technologies that you use daily have hidden historical roots? Your car, your smartphone, your computer, all contain components and designs whose development history is complex and fascinating. Technology is never just the present, it always carries the past within it. History has a bitter irony. Germany lost the war. Its factories were destroyed. Its scientists scattered. Its patents stolen. But the technology survived. Carl Zeiss precision defined a standard that the whole world adopted. Allies who conquered and copied Carl Zeiss thereby confirmed its superiority. Every modern optical device that uses Carl Zeiss principles is a monument to German engineering. What the American soldiers found in that Jena factory in 1945 was more than just equipment. It was a scientific legacy so valuable that it survived 3 generations. German precision in glass and lenses, translated into mathematical formulas and manufacturing processes, became the foundation of an entire industry. The Allies didn't just plunder Carl Zeiss. They recognized its genius and made it the standard. A British optics expert wrote in 1947, "We have spent years studying and copying Carl Zeiss. Now we finally understand why German optics was so superior. It wasn't a secret, but an entire system of science, engineering, and industrial precision. We can now replicate it, but we didn't invent it. That was German genius." This story should be known to anyone who looks through a camera lens, peers through a microscope, or uses a telescopic sight. The technology they take for granted has a history of scientific brilliance, war-driven superiority, and post-war technology transfer. Carl Zeiss didn't just create products. He created a technological revolution whose impact is visible to this day. The next time you take a photo with your smartphone, remember this. The coated lenses that make the sharp image possible are based on technology developed in a German workshop. The mathematical formulas that optimize the lens design were written by a German physicist. The glass composition with precisely controlled optical properties was invented by a German chemist, Carl Zeiss. Defined precision optics. Allied forces captured Zeiss, and the entire world benefited from German technological legacy. This is the true story behind every modern optical device, a story of innovation, superiority, plunder, and ultimately, the global spread of German engineering. What surprised you most about this story? Did you know that your smartphone camera is based on German optical technology? Share your thoughts in the comments below. And if you want to learn more about German technology that shaped the modern world, subscribe to the channel. History isn't just the past, it's all around us, hidden in the devices we use every day.